Okay, so welcome all. It's a pleasure to introduce you to Professor Lizy John. She is the head of the Laboratory for Computer Architecture at the University of Texas in Austin. And she's well known for her work on workload characterization, performance evaluation, recursive computing. A well-recognized researcher in this area. And we are very happy to have you here. Okay, so welcome, Lizy.
Thank you, Gita. And I'm very happy to be here too, but my throat is a little, so hopefully it cooperates until I finish the talk. So in this talk, I basically have a few examples of machine learning applied to performance evaluation. And before getting into the talk, I want to acknowledge the opportunity to work at the University of Texas and being able to work with people like John Goodenough, who won the 2019 chemistry Nobel Prize, but he was one of our colleagues. He invented lithium rechargeable batteries. And then also Bob Metcalfe, who won the Turing Award last year. And also all my wonderful students who worked on the many topics. So I do computer architecture, performance evaluation, machine learning now, but these are a few examples of dissertations, so you kind of get, the breadth of the topic. But I'm going to focus only on the performance evaluation and use of machine learning for it. I don't know whether you can hear me at the back. Okay, yeah. And my research has benefited from many sponsors and the many wonderful grad students I have worked with. So for today's talk, 3 examples on performance modeling and prediction, performance or power. And the first one is a calibration of power models you make. They have errors, how to calibrate it and make them more correct using machine learning. The second one is, can you use one computer and run workloads on 2, but use one to tell the performance of the next generation? So because you can simulate the next one, but it's very slow. But if you can run on one, then you maybe at real speeds, then you can estimate the performance faster. So cross-platform prediction. And if we have time, I'll go into a third one, which is about stress benchmarks and using machine learning. So the first one, in computer architecture, we use a lot of simulations, many simulators, some combined with some analytical estimates for the power modeling, etc. So MuckPat is a very common power modeling tool which uses activity metrics from simulation and some analytical things corresponding to the configuration, and then estimates the power. But the estimated power is that blue line over there. Often if you would make hardware for that same corresponding configuration, you will see that you are wrong. And that error is like not small, 30, 35, 40, 50% sometimes. So the real measured power is like the red line, and the MuckPat's modeled power is like the blue line. But we can run many workloads on both and try to see what is this correlation for the error. So the workload, from the workload features, if you can derive what is the error, then you can correct it. So this is done using regression, and 20, 30 workloads are fine. You don't need big data. Training, you don't need huge amounts of data. And the idea is to basically, in MuckPat, it uses many weights in order to, for each activity, there is a certain weight with which you are multiplying to find how much will the power be. So during training, you derive the corrections for the weights and then use those new weights, and with you can you make both the calibrated power and the measured power be the same. That's the idea. The regression, correcting each of those coefficients, has to be done with a few workloads, and this basically you see that there are corrections needed additively and multiplicatively. Both there are some are just a bias, so you can add the correction. Some are not simply bias, but it is based on some other thing. So you could use, what am I doing?
Okay.
It's okay.
It's exactly that.
Okay. Yeah, so the corrections are applied. So we used the non-negative least square error solver in order to find the corrections. So you need to have the features measured. So one is a hardware on an Odroid board with the ARM DS5 measurement tool. We were able to obtain the features. And the features, generally we just measure very basic things about the workload, L1, L2, cache features, branch prediction related features, number of instructions, instruction mix, etc. And the correction factors are derived using the non-negative least square error solver. And with that, we can actually correct most of the errors in the difference between the real and the measured. So things that used to be 30% or more now are down to less than 5%. And two different calibrations were applied, and those are the two greens, but both are pretty good. But the yellow is the one without any correction. So that's just one example of how this could be done with regression. And this is not only correction in the whole workload, like at the end, because if we were to estimate the energy consumed by the entire thing, there are many places you could have plus and minus errors cancel each other. This is not like that. You can see on a time scale, when the power is going up or down, our models are tracking that pretty well. The correction does work in that situation. So that's for the first example. Any questions? Feel free to interrupt me. Okay, we'll go to a second example. This is, we use simulators a lot in computer architecture. And these simulators are really slow, and they cannot run every workload because only some runtime systems won't run on the simulators. Java is a very common example. Many simulators won't even be able to handle it. So let us say we have a host machine, which is a real machine, the previous generation, but its speeds are much better than the simulation. And then we have a simulator for this next generation machine we are building. The next generation machine, that simulator, has the hardware features of whatever we want to model. So we can get estimates from that, but we cannot run many real workloads on that simulator. Or they take a month or something like that to run, and that's somewhat prohibitively expensive. Can we run some smaller workloads on both the platforms and then obtain the performance or power feature vectors on the host machine as well as on the simulator? So the simulator vectors are the ovals. The real machine hardware that's available already are shown with those lines. Now if a statistical model can learn from those two sets of features, and the workload features also, so whichever workload feature leads to what kind of performance features. If you have enough samples, and here you needed more samples than the previous one. The previous correction, that worked well with 20 to 30 training programs are enough. Here you would need more. And so once this model is obtained for a new workload, which is very complex, maybe Java or maybe Hadoop, whatever things, which can run on this machine, because this is a real machine, just not the machine we are designing, something that's on our desktop. We get these vectors, using these vectors and that model, we can predict the vectors in the oval. Okay, that's the basic idea. We applied this to estimating cycle time, estimating power or energy in the context of a full machine. That was this work. Recently, we have also been doing this at the context of RTL model in hardware power estimation from one FPGA to the next generation FPGA. So this is pretty general, the idea, cross-platform performance or power estimation. And so here, the technique that was used here was piecewise constrained lasso, and until it took a while to get to the right technique. Simple regression never yielded good accuracy. So basically the model, the whole thing is from one platform to the other, it's not necessarily a linear correlation. So you can't solve it very easily. However, in the neighborhood of where this machine is, there it's linear in a small area. So you have to first identify where you are, and if there are enough points in there, and the number of points, we need at least 150 in the neighborhood in order for it to be successful. If you have very few points and you only saw, if there aren't enough points in the neighborhood, you won't be able to get the, good accuracy. So where did we get the training set to do something like this? So we use the ACM ICPC programming contest database, which contains lots of programs in many different application domains. I would argue that a large number of algorithms, types of algorithms, and data structures that are commonly used in coding, they all appear with these different sets. So we thought, let's try whether that'll work. So we used these programs to train, and the test set that was used was spec CPU programs. So nothing from spec was ever used in training, but training was only the ACM ICPC database. And for each of these programs, you can give multiple data inputs, and you can generate more data that way. So this adds to roughly 150, but we created almost more than 2,000 or close to 3,000 samples with different data sets or with different data inputs to this program, something like that. So the features that were taken are things that we can measure on the machine that we are training. We used Intel x86 to train, and then we estimated performance on an ARM processor. Similarly, we also trained on AMD and estimated performance on ARM. So in both cases, the estimate was on ARM, and the training was either on Intel or AMD. Both don't have exactly the same kind of performance counters. On AMD, some things were not available, the same thing. So AMD, we only use about 8 or 9 counters. Intel, we had about 14 counters. And so we wanted to see whether if you only had the basic things like in the AMD, can we still create this model? That was part of the idea. And what we find is very good or very low prediction errors this is for performance. And this one, the first one is the cycles predicted on ARM, but based on training from Intel. Here the training is from AMD and predicted is ARM. And the third one is the actual cycles on ARM. Now, the errors, I guess we can just look on the red and the blue lines to see how much error. In total number of, basically the prediction error is 2%, less than 2 or 3%. And that's extremely good. But we didn't, one of the things is the error can be a lot more. The error depends on how many points you have in that neighborhood to be able to find that linear region inside that curve. And so this showed the errors could go up. It also, until there was, first we used lasso regression, and our errors were very high also. So finally, until we found the piecewise, the lasso, the errors were high. And I would say from the earliest regressions we did up to the PCL SLR method and this low error, perhaps it was about 2 years. We tried many things. And the interesting thing about this work was the work was done by a student who was not a computer architecture student. He was in the software engineering. He just saw all the architecture students doing these simulations. He said, I can predict this. I know I can. So it was a challenge he took on to himself, and he decided to do research in this just because he thought it didn't make any sense to simulate for weeks to get one data point. It should be doable in some other way. So somebody who doesn't have the domain knowledge, so he doesn't know to pick the measures that need to go in. He would have, oh, what should I pick? So it was an interesting piece of research. Here also, with the time varying, we could basically see that power and performance, in this case, cycles, so performance is tracking the actual pretty well. And for power also, it's tracking it very well. Now, so this cross-platform prediction, it can be for any objective metric you are trying to find, and it can be between any different platforms. At this point, we have work going on about FPGA power. So if you are using a certain FPGA and you are going to move to something else, how much would you get? We could quickly predict that before buying it. If you could generate certain metrics and get the correlation. And this can probably be applied to many, many things, but this one was definitely encouraging. Okay, any questions? All right. So the next one, this is about stress marks, power stress mark, or thermal stress mark. Essentially, hardware designers are worried that someone could run some software to get the power above what they have designed it for. So the question, there is something called thermal design power. And there is also, if you took every functional unit in your design and added up the power, there is a totally different number. That number is very high usually. No one designs for that power, because if you design for that power, then the external current that needs to come to your computer may not even come through. Our walls have to be rewired, everything has to be rewired, because that power is a really high number. So designers found you never have to design for such a high number, because usually, let's say CPU is running at its highest, at very high utilization. Most of the time memory is not working because the data is in the cache. That's why it is running at that good utilization. If you have a lot of cache misses and you are going to the memory is working at higher speed and CPU is idle. So there is no need to design for the sum maximum of everything. So they don't design for it anyway. But when you don't design it for the maximum of everything, it is a worry whether someone would somehow drive it. and create a virus to basically, maybe that was the wrong word to use. So the virus can drive the power to very high numbers. So this work is basically creating automatically a stress mark, drive it to the maximum to see, even if you had any kind of program that would drive everything at the same time, can it really go up like that? That was the idea. And here the idea is that, and so the reason we reach there is in our workload characterization work, we had actually created mechanisms to copy a program or make a proxy for a program. The idea, so I'll come back to the other slide again. If we have a program, can we make a tiny performance or power clone for the original program, which is very big? This is also another solution for simulations taking too long. If, let's say the spec workload runs for 18 hours, can I make something which is equivalent in performance and power and runs in 10 minutes? Is it possible? So we had worked on that topic. And in that, basically what we found is we can create a synthetic program which has approximately, except the size, we always wanted to miniaturize, but it has the same instruction mix, or it has the same program locality, it has the same control or similar control flow behavior or parallelism or communication or data sharing patterns. Any of the features that you think is important, if you could feed all these features, I want a program with this kind of instruction mix and this type of locality behavior, and the synthesizer creates a program like that. Now, if we want to make a stress mark, all we have to do is those knobs turn it to weird values, not necessarily values corresponding to the program I'm trying to clone. Here I'm not trying to clone anything in specific. So drive the knobs to weird values, basically, to see whether I can create a really bad program. Bad program in the sense something that will drive the power to very high values. So the way this proxy itself worked is we use statistical flow graphs. Real programs have control flow graphs, but if you analyze all of the basic blocks and the control flow graphs, you can see that many places are similar. So statistically, you can model that and say, if I have a program with a mix of this kind of basic block, these kinds of basic block, and frequencies of going from this nature to that, so some such principles were employed to basically make the proxies. And the features that were used are the kind of features we already talked about: instruction mixes, dependency, locality, data sharing, such things. And you use that statistical flow graph elements, basically create a template, fill it in, adjust it to get the features that you want. And so we were making proxy benchmarks already, which could give for performance 3% error, for power this is 15%. But now we could use the same principle and create some synthetic programs, feed it to if I want to make a stress mark for an x86 that's on my desk, feed these synthetic programs to basically either a simulator or an actual platform. You get what are the power or performance metrics for each of these synthetics, give it to a genetic algorithm, that's what we used in the machine learning block, and that kind of finds some knob values which are different than what I used already. Using those new set of knob values, you generate another code, feed it in, you go a few iterations, you can come up with what is a possible stress mark you can make. So when you look at stress marks that are out there, that are used in industry, most of them are basically x86 assembly based. So Intel has all these kinds of programs and AMD has these kinds of programs. they are all using a assembly language, because if you write in C, by the time you compile, you don't know exactly what you are getting. So they inline assembly and these are written by domain experts, hardware designers who really know, oh, this float, if I do a floating point multiplication with 16-bit data, 64-bit data, it will consume the highest power. So they put in a few of those. But if you need to have the data in so they interleave it with something else in order to create it. So now, if you want to write a program in C, M prime, Mersenne prime generation, that's apparently one of the programs, no matter which platform you run, it takes very high power. Now, our objective is to find something like this, but without knowing anything about the hardware, just find it automatically. And so these are all programs that existed, we just characterized and saw their power. Now we want to exceed this or make something using genetic algorithm and the methodology I explained before. We are going to automatically find something that takes more power than the other programs. And the genetic algorithm, with its mutation, crossover, its operations, you basically, irrespective of where you start, in a few iterations, this is the M prime number, M prime power, it exceeds M prime and it keeps going, and after some point it's not improving much more, so we stop. But so the blue line is obtained without knowledge of the hardware, and and it is better than, how much better is it compared to what you can find compared to the spec benchmarks. Basically we could find much higher power. So somebody can, if you look at the spec programs and the one with the maximum amount of power, if you think that may be the most, that's not correct. There is much more somebody could do by writing a program, but it is still much less than if you add up all the units. Okay, and for a particular, and this is again another example where the power that we can get automatically is much higher than all of the others. And for this one was where we had an actual hardware, and the hardware, this was a K7 machine, and there is a Bern K7 program existing, which was written by somebody with the domain knowledge, and we are able to exceed it at least some. It's not the improvement on the last bar is not much higher than this, because this is written by somebody who really knows the machine, and they have really done a good job. But we still automatically could find something that was slightly higher. And I actually have talked to some of these people whose jobs are in their companies to write these programs, and they said, yeah, it's good to have such a methodology because I lose a lot of sleep. They lose a lot of sleep over, yeah, I think I did a good job, but who knows whether something else can be made. Okay, and we did this on single core as well as many core machines. The single core work was called SIMPO, this one is called MAMPO, and so on. So essentially, a lot of problems in performance evaluation, we could use machine learning to either to correct models or to create models to estimate things without, where detailed simulation, cycle by cycle simulation would be very expensive. So I have a few examples. That's what I presented. If any questions, please ask. Okay.
Thanks a lot.